Hello, calculus students. So I want to carry on with the problems that we didn't quite get to in class today so that you can have some more practice on solving these derivatives with logs and natural logs in them. So I'm going to do one more of these kinds of examples. If you remember, we left off by looking at expressions here that we can simplify using these log laws up here. So for this one, I'm going to rewrite this a little bit. This is the same as ln of x times 3x minus 1 raised to the 1/2. So the first thing I'm going to do is I'm going to use the product rule. So it looks like this. The log of two products is the same as the sum of the logs. So y is equal to, let's zoom a little, y is equal to ln of x plus ln of 3x minus 1 to the 1/2. And then with the power rule for logs, I can bring down that half. So y equals ln of x plus half ln of 3x minus 1. Now, I can take the derivatives using very simple natural log derivative. I can use the simple natural log derivative. So y prime equals 1 over x. And usually I would multiply by the derivative, but the derivative of x is just going to be 1 plus a half. And then 1 over 3x minus 1 times the derivative of that, which is 3. So just to simplify a little more, it's 1 over x plus 3 over 2x, 3x minus 1. So I just kind of combined terms here. I want you to try these other two, 16 and 17, on your homework. So this is going to be homework. This is homework. And then down here, I'm going to show you how to do what we call logarithmic differentiation. Okay, so to find dy dx for this thing, it sort of looks like, oh, why can't I just use the product rule and bring that down? That only works when the exponent is a coefficient or an integer. So if I had x to the 5th, then I could do the power rule. But with this, I can't. So logarithmic differentiation means that we're going to solve this by first taking the natural log of both of these sides. You will see why. Because when I take the log of both sides, it solves the issue that I have with this exponent. Because the exponent is what's making this difficult. We don't know what to do when we have an exponent of x. Don't know how to solve an exponent of x. So when I rewrite this as a log, now I can use my log laws to make this more simple so that I have ln of y equals x times the ln of x. Because with my log laws, I can bring down the power. So now I no longer have that exponent. It's down here. Now this is just a product rule. So I can differentiate this. I'll have to differentiate implicitly since I don't have this solved for y. So I'm going to have to use implicit differentiation. So on the left side, I'm going to have 1 over y dy dx. And over here, I'm going to use the product rule. So I have x times 1 over x dx dx plus 1 times ln of x dx. And my dx's go away. So I have 1 over y dy dx equals, this just goes to 1. And this goes to ln of x. So to solve for dy dx, I'm going to multiply both sides by y. Multiplying by y, multiplying by y. And I get y. What's this? Oops, I don't know why I wrote it like that. This is just ln of x. And I need to use parentheses to multiply the whole thing by y. And then I can substitute this in for y, so that I only have it in terms of x. And I get dy dx equals x to the x times 1 plus ln of x. This is logarithmic differentiation, because I used logs first, the natural log, to fully solve for this, to get rid of that exponent.